Okay, let's take a look at the calculations involved in homework number 1. Um, we have data here for 3 runners on their rate of oxygen consumption, VO2, and their rate of carbon dioxide production, VCO2, to run at a certain speed here, 3.9 meters per second. You don't really need these speed numbers here to do any calculations in this homework. This is just shown so that you can see that each of these runners they were all running at the same speed. Because if you want to compare apples to apples for running economy, then you want to be comparing people doing similar external workloads, so running at similar speeds here. So that's just included so that you can know that there's no speed differences that might explain any differences in the numbers that you calculate here. Think back to the Joyner paper, one of the early papers here in the running section on class, where there was 3 parameters that can define somebody's theoretical endurance running ability. Those 3 parameters were VO2 max, lactate threshold, and running economy. Now, a common mistake students will make on this homework is they see this symbol VO2 here and you immediately start thinking VO2 max. Okay? That's incorrect for this particular homework. These numbers here for VO2, they are not the VO2 max values for these athletes. Okay? VO2 max is assessed in a graded exercise test where you start the exercise at a low intensity and you gradually ramp up that intensity to determine what's the maximum rate at which that runner can supply oxygen to their body. Okay? That's not what was done here. These are not data from the maximum rate of oxygen consumption for a graded exercise test. These are data where these individuals were running at this steady submaximal speed and measurements of their rate of submaximal VO2 and submaximal VCO2. Okay, so don't take these numbers here and interpret them as, oh, VO2 max, I want that to be high and that's good. That's true, you want a VO2 max to be a high number to be a good runner, generally speaking, but that's not what these numbers are here. It's their submaximal oxygen consumption running at a submaximal endurance type speed. It's not their VO2 max. Okay? Now, for running economy, the way that we assess that is with a test like this. You put somebody on a treadmill at some speed and you measure their rate of oxygen consumption, their rate of carbon dioxide production. And from that, with an equation like this, you can calculate their metabolic rate. Okay? And for running economy, to be a good economical runner, you generally want your VO2 and your VCO2 and your metabolic rate to be low. Okay? That indicates that I don't need a lot of fuel, I don't need a lot of energy to perform this effort, running on this treadmill at this speed, and that indicates somebody who's a good, efficient, economical runner, somebody that uses less energy to hold a certain speed than somebody else is generally a more efficient and more economical runner, and that's a good thing for running performance. It suggests you have a large capacity to go faster, to go harder. Okay? So that's the first calculation we're going to make here, is we have measures of oxygen consumption and carbon dioxide production. We can plug those into this algebraic equation here to calculate this person's metabolic rate. Now, this metabolic rate, what is this exactly? This is a estimate of the internal energy decrement in the body when running at this particular speed. And what do I mean there, internal energy decrement? Internal energy here is the food energy stored in the body in the form of the macronutrients in the food that we eat, carbs and fat and protein. That energy, that food energy, gets converted to chemical energy, which is the energy that powers the chemical reactions involved in metabolism, muscle activity, and other organs as well, involved in sustaining life while performing exercise like this. Okay? Now, where does the equation like this come from? These numbers here, like 0.276 and 0.075, like where are those coming from exactly? If you take those 3 main macronutrients, carbs, fat, and protein, and like combust a unit mass of each one of them, like if you take a gram of carbs versus fat versus protein, each one of those, when you combust them, consumes a known amount of oxygen and produces a known amount of carbon dioxide. Okay? And if you then make some kind of hand-wavy assumptions about what's going on with protein, which is not something that is used a lot, as or at least doesn't vary a lot as a fuel source in normal human metabolism, you can back out an equation like this that relates the whole body oxygen consumption and the whole body carbon dioxide production to the whole body rate of metabolic energy expenditure. Okay, so that's where this equation comes from. Now, first thing you want to do to proceed with this homework is calculate for each one of these runners from their VO2 and their VCO2, what's their E dot, what's their metabolic rate. Okay. You can try copying and pasting this table into like a spreadsheet here. I'm going to do these demonstrations in Microsoft Excel, but it should work fairly similarly if you're using something like Google Sheets. You can try just taking that table and copy pasting it here. It looks a little ugly, so I'm going to just copy this over by hand. I've got these three runners here, runner 1, runner 2, runner 3. And for each one, I've got their VO2, VCO2, and their mass. And I should include units on these things. VO2 is ml per kg per minute. And same for VCO2. Okay, and then let's just copy over runner 1's values here, 45.7 for VO2, 40.7 VCO2, 66.7 for kilos. Okay, and then E dot for that runner, watts per kg, would be calculated using this equation here. So I'd do equals 0.276 times VO2 plus 0.075 times VCO2, and that gets me a value of about 15.7. And if I look at my prompt down here, it says if I'm doing this right, I should get numbers of roughly 15, 16-ish watts per kg if I'm doing it right, so I've got some confidence there that I did that right. So repeat those calculations for these other two runners here and get an E dot metabolic rate value for each one of those runners. And that's one of the numbers that you need to proceed with answering these questions down here for this homework. Another calculation that it'll ask you to do is this respiratory exchange ratio, which is the ratio of carbon dioxide production to oxygen consumption. That's RER, and that's VCO2 divided by VO2. If you've taken KNES402 already, exercise physiology, you're probably pretty familiar with this variable. If you're not, what this is calculation-wise, I just did it, it's the ratio of VCO2 to VO2. It varies from about 0.7 to 1. The lower it is, and this relates to like where do these numbers come from in this formula up here exactly. The lower RER is, the greater fraction of this metabolic energy is coming from fat as an energy source, and the higher RER is, the greater fraction is coming from carbohydrates as an energy source. Okay, and then at kind of intermediate values there, then you're using a mixture, a combination of both fat and carbohydrates to produce that metabolic energy that you're using to power the chemical reactions involved in metabolism and exercise. Okay? I forget the exact numbers here, but like the lowest this could ever be is something like 0.7-ish, which would be a case where you're using exclusively only fat as the metabolic fuel, and the highest it could be is about 1, which would indicate using exclusively carbohydrates as fuel. Now those extremes won't happen often in like actual real metabolism. It's hypothetical cases where you're only using one particular type of macronutrient there as fuel. But that's the basis for like if you're ever like on a treadmill and you see it showing like a fat burning zone and a carb burning zone, and the fat burning zone is usually at like lower speeds. The lower your RER is, the lower the fraction of energy coming from carbohydrates, and the higher the fraction of energy coming from fat. And then the higher the RER is, the higher the fraction of energy coming from carbohydrates, and the lower the fraction of energy coming from fat. This is generally used as an index of like the intensity of exercise. The lower the RER is, generally the lower the intensity is, and the higher the the RER is, generally the higher the intensity is. Like this is one of the variables we'll look at for doing like a graded exercise test and assessing if it was truly like a maximum effort for somebody. You should see this like creeping up near and maybe even a little bit above 1.0, indicating that this is an intense type of exercise. So somebody that has a high RER here, regardless of what, VO2 and E.R, if the RER is high, that's an intense exercise challenge for that particular person. Another calculation that you might find helpful here in doing these comparisons here is this scaling by body mass. Notice here we have the metabolic rate and the rates of pulmonary gases here expressed as per kilogram per unit body mass. If you want to unscale it and just get it in net watts, regardless of how heavy the person is, you can just simply take that E dot value, metabolic rate in watts per kg, multiply it by the kgs, and then you get it there just in straight up watts like that. That'll be another calculation that you might find helpful for doing this particular homework here. Okay, so I walked you through doing that for each one, or for this runner number 1 here. You'll want to repeat that for these other 2 runners. Like for runner 2, you do 41.49 for their VO2, 41.1 for their VCO2, 74.4. And you can just copy paste these cells here and then repeat that for runner 3 with their numbers, and then you'll have all the numbers that you should need to do this particular homework.